Welcome to the deep dive. Today, we're trying to get inside the head, well, the high-dimensional space of large language models.
hmm
That question everyone asks. When they give you that step-by-step answer, that chain of thought, is it real thinking? Or just, clever mimicry?
It's the ghost in the machine question, updated for AI.
Yeah.
People have wondered about this for ages. Remember Thomas Hobbes? Reasoning is nothing but reckoning.
Right, calculation. But what does that calculation look like inside an LLM? How does it work geometrically?
That's what we're digging into. We've got this fascinating paper, The Geometry of Reasoning,
What?
Flowing Logics in Representation Space.
Okay, so we're moving past the whole stochastic parrots debate, trying to find some actual measurable evidence of logic.
Exactly. And the claim here is pretty bold. It suggests reasoning isn't just a sequence of steps, like hopping between points.
Okay, what is it then?
It's more like a continuous, smooth flow, a trajectory. And the really crucial part, the shape of that flow, its geometry, is controlled by formal logic.
Regardless of the topic or the language.
That's the claim. It's supposed to be an invariant. And they've got empirical evidence using models like Qwen3 and LMA3.
All right, let's break that down. Reasoning as a flow. We kind of accept already that concepts live in this geometric space in LLMs, right? Like cat and dog are closer than cat and car.
Yeah, that's the embedding space idea, meaning represented by position.
So the paper's hypothesis is that reasoning, going from premise A to conclusion B, is literally tracing a path through that space.
A continuous path, a trajectory. It actually reminds me a bit of William James.
The stream of consciousness. It flows, a river or a stream. Is that the metaphor we should be thinking of? A thought river in embedding space.
It's a good starting point, but this paper gets, well, much more mathematical, differential geometry, actually.
Okay, so how do they measure this river?
They track what they call the context cumulative trajectory, which basically means at each step in a reasoning chain, say a chain of thought process,
Yeah.
they record the model's internal state, the embedding vector for that step.
So snapshot 1, snapshot 2, snapshot 3. And connecting those gives you the path.
Exactly. You trace the evolution of the model's internal representation. And the key hypothesis is that this path is smooth, mathematically C1 continuous. It doesn't just jump around randomly.
Which is different from how people sometimes thought about it before, right? Like a random walk on some kind of graph.
Yeah, some earlier views might have framed it more discretely or stochastically. This perspective argues no, the flow is structured, it's directed, it builds on itself.
Okay, but the huge challenge must be proving this flow is driven by logic, not just, words that sound similar or topics that are related. How do you filter out the noise?
That's where the experimental design gets really clever. They call it the SMART test. And it's all about disentangling the formal structure from the surface content.
Disentangling logic from semantics? How?
They started with abstract logical skeletons. Think of basic logical patterns like if A, then B, A, therefore B, but more complex ones based on natural deduction systems.
Just the abstract structure, no specific meaning yet.
Right. Then, and this is the critical part, they took the exact same logical skeleton and filled it in or instantiated it using vastly different topics.
How different?
20 different domains, weather, finance, network security, education, ancient history. Really diverse stuff.
Wow.
And not just different topics, but also different languages.
Mm-hmm.
English, Chinese, German, Japanese.
Okay, hold on. If you apply the same logical steps to, say, finance and weather, isn't there a risk the model just kind of fakes it, or that similarities pop up just because the structure sources it?
That's what they needed to test. But the key is that the words and concepts were completely different. The only thing held constant across these examples was the underlying formal logical structure, the pattern of dependencies between the steps.
Can you give that example from the paper? It helps make it concrete.
Sure. Let's say you have a 9-step logical argument. In the weather domain, step 1 might be something like if moisture converges, then thunderclouds develop.
Okay, A implies B.
Now, take that same first step in the 9-step structure, but apply it to finance. It becomes, if interest coverage exceeds 3.0x, the bank approves the loan.
Ah, I see. The function A implies B is identical, but the content, the actual meaning, is totally different.
Totally different, and potentially in a different language, too. So they generated pairs of these reasoning chains, same logic, different content, fed them to the LLMs, and then measured the similarity of the paths the model took internally.
And they looked at similarity in different ways, you said. 3 orders.
Yep, 3 geometric orders.
Just
0 order is just position. Where's the embedding vector located in the space? Its absolute coordinates.
okay. Static location.
Then first order is velocity. That's the change from one step to the next. Think of it as the speed and direction of the thought at that instant.
The local movement. Makes sense. And second order.
That's curvature. How sharply is the path bending or turning at that point?
Curvature. That sounds important. They use something called Menger curvature. Why that specifically? Why not just measure the angle change, like with cosine similarity?
Good question. Cosine similarity just tells you about the change in direction. Menger curvature is more sophisticated. It's based on the circle that passes through 3 consecutive points on the path.
Okay. What did that capture?
It captures the intensity of the reasoning step, geometrically. It couples both the angle of the turn and the distance covered during that turn. It's not just if you turned, but how sharp and significant that turn was relative to the step size.
So like steering the wheel and hitting the gas at the same time?
That's a decent analogy, yeah.
Mhm.
It gives a richer picture of the local dynamics than just the angle alone.
All right. So they measured these 3 orders of similarity between flows that shared the same logic but had different topics or languages. What did they find?
Well, the zero-order results, the position, were kind of predictable. They were overwhelmingly dominated by the surface stuff, the semantics,
Yeah.
meaning embeddings clustered by topic and language. Using their Quen 3 example, the language similarity score was high, like 0.85. If the model was talking about finance, its internal state was in the finance neighborhood of the embedding space, regardless of the specific logical step. Logic similarity at this level was low, only 0.26.
Okay, so if you only looked at the location, you'd say, yep, it's just grouping similar words. Content is king.
Exactly. But then they looked at the change of the velocity and especially the curvature, the first and second order similarities.
I did.
And that's where the logic shone through. The surface semantics, the topic and language, their influence dropped dramatically. Logic became the dominant factor, explaining the similarity in the dynamics of the flow.
Give us the numbers for curvature. That was the key one.
Right. For Quen 3 again,
Yeah.
curvature similarity based on topic was just 0.11. Based on language, 0.13. Pretty low.
Mm-hmm.
But curvature similarity based on logic jumped to 0.53.
Wow. That's a huge difference.
It's strong evidence. It confirms the hypothesis. The topic determines where you are in the space, roughly. But the formal logic dictates how you move, how the path bends and turns moment by moment.
So it doesn't matter if it's reasoning about history in German or finance in Japanese, if the underlying logical step is the same.
The geometric dynamics, the way the internal state shifts and curves, is structurally similar. The logical operation acts like a local controller for the flow's velocity and curvature.
It's like the LLM has internalized this universal logic separate from the words themselves. It's embedded in the model's dynamics.
That's the interpretation. It suggests a deeper kind of understanding beyond just surface patterns. The paper argues this emergent acquisition of universal logic is a potential hallmark of genuine intelligence.
Especially since it took humans, millennia to formalize logic, and these models seem to find it geometrically just from data.
It definitely complicates the stochastic parrot narrative. This continuous, geometry-driven view seems hard to explain if reasoning is just discrete, random jumps between states.
And the practical side of this. If reasoning is a trajectory, what does that mean for controlling these models, for alignment and safety?
It opens up really interesting possibilities. Current methods often focus on nudging static vectors, like changing a single concept's representation.
Right. Vector steering.
But if reasoning is a flow, maybe we can intervene on the dynamics themselves. Think about guiding the entire trajectory, not just a single point. Maybe you could influence the curvature to keep the reasoning on a safe or desired path.
Steer the thought process itself. That's fascinating.
It could also inspire new model architectures. Maybe models explicitly designed to work with these latent flows could lead to more efficient reasoning, maybe different kinds of memory. Who knows?
We're shifting from just looking at the final answer to analyzing the physics of the thought process along the way.
That's a great way to put it, the underlying physics.
Okay, so the key takeaway for you listening is this. When an LLM seems to be reasoning step by step, it's not just linking words. Internally, it's tracing a kind of smooth geometric path. And the formal logic isn't just decoration. It acts like the hidden rules, the differential constraints that govern how that path twists and turns.
Yeah, the logic shapes the flow, which leaves us with a pretty deep question to ponder.
Go on.
If these models can spontaneously internalize the abstract structure of logic as a geometric invariant, what other abstract non-linguistic structures might they have learned? Could they have developed geometric representations of things like, say, morality? or basic physical laws? And could we measure their curvature?
Measuring the curvature of morality in an LLM. Now, that is a deep dive for another time. Thanks for walking us through the geometry of AI thought.
My pleasure. It's fascinating stuff.